In this video, we'll introduce sampling distributions and estimators. Key idea is that we're going to be working with statistics rather than values from the original population. We'll deal with statistics computed from samples. So the general idea is that sample proportions and means, and other statistics as well, tend to be normally distributed, and the mean is going to be the same as the population mean. Here's a graphic illustrating what's going on. You have a whole bunch of samples, and you take the sample proportion from each of them, the percentage of Mainers that have a snowmobile. So you have a whole bunch of sample proportions here, and you wonder how those are distributed. And you could do the same thing with the sample means. Notice the notation here. X bar is your sample mean. P hat means that it's an estimate of the actual population proportion. Or we could do the same thing with variances. So statistics describe samples. It's a number computed from a sample. Means and proportions will be the two that we mostly look at. So if we know how the sample distribution is, what it looks like, we can answer a question like this. Right? And often we don't know those population parameters, and we estimate them using statistics. So knowing about the sampling distribution can tell us about the accuracy. So the sampling distribution of a statistic is a distribution of all possible values of that statistic when you consider all possible samples of the same size n. For example, we could look at the sampling distribution of the sample means. We imagine all sample means taken from all samples of size n. A little bit of notation. We use symbols above letters to designate numbers computed from a sample. So p hat is a sample proportion. The behavior of sample proportions and means, well, they tend to be normally distributed. And actually that will hold if the original distribution is normal, or if the sample size is bigger than 30. Also, the sample proportions and means are unbiased estimates of the true proportion and mean. So they tend to target the true population values. More precisely, the mean of the sample means is the population mean, right? And the mean of the sample proportion is the population proportion. So we say that they're unbiased estimators. Okay. The standard deviation, on the other hand, is not an unbiased estimate. It is biased. So it's kind of interesting that the sample variance is unbiased, but the standard deviation, which is just the square root, is biased. It's just a peculiarity. Okay, estimator is just a statistic that we use to estimate something else, usually a population parameter or proportion. Okay, so this is what we just said. Unbiased estimator tends to target the actual parameter we're trying to estimate. Here are some examples of unbiased estimators: proportion, sample mean, and sample variance. On the other hand, these are all biased estimators. It's easy to see why, for example, the sample maximum would be a biased estimator. You're most likely, with a sample, the sample max is going to be something less than the population maximum. So the sample maximum is going to tend to underestimate the population maximum. Similarly, the minimum would tend to be an overestimate of the minimum. So the range would also be biased, and the median is a biased estimator as well. So this has been a basic introduction. Next up, we'll use the central limit theorem to find probabilities for sample means.